Niels Bohr's groundbreaking work on the hydrogen atom marked a turning point in the history of physics, bringing a new level of clarity and precision to the understanding of atomic structure. In the early 20th century, scientists were still grappling with the mysterious nature of atoms. While the basic structure of the atom had been proposed, an atom consisting of a dense nucleus surrounded by orbiting electrons, there were still many questions that remained unanswered. Atoms, it seemed, were not just simple, indivisible particles. They exhibited strange behaviors, especially in the way they emitted and absorbed light. The prevailing theories could not fully explain these phenomena, leaving a significant gap in scientific understanding. This is where Bohr's model came in, offering a fresh perspective that would forever change atomic theory. Prior to Bohr's discoveries, the behavior of electrons within atoms was not well understood. Classical physics, based on Newtonian mechanics and Maxwell's electromagnetic theory, suggested that electrons should orbit the nucleus in continuous paths, like planets around the Sun. However, this theory didn't match the observations made in experiments. When scientists studied the light emitted by atoms, specifically hydrogen, they found that the light came in distinct, quantized lines, rather than a continuous spectrum. This presented a major problem for classical physics, as it could not explain why atoms emitted light in such discrete amounts, known as spectral lines. The failure of classical physics to explain these phenomena led to the need for a new theory. It was clear that a deeper understanding of the atomic structure was required, one that would account for the peculiar behavior of light and the interactions of electrons with the nucleus. The key to solving this problem, Bohr realized, lay in applying the emerging ideas of quantum theory to the atom. The quantum theory, which had been introduced by Max Planck and further developed by Albert Einstein, dealt with the idea that energy is not continuous, but is instead quantized, meaning it comes in discrete units, or quanta. Bohr built upon the work of Planck and Einstein by applying quantum theory to the atom, particularly to the hydrogen atom, which was the simplest and most well-understood atom at the time. He proposed a model in which electrons orbit the nucleus in fixed discrete orbits or shells, each with a specific energy level. This was a major departure from classical physics, which treated electrons as particles that could occupy any orbit. Bohr's model, however, posited that electrons could only exist in specific orbits, each associated with a quantized energy level. These orbits were not random or continuous, but fixed and well-defined. The idea of quantized orbits was the key innovation in Bohr's model. According to Bohr, the electron in a hydrogen atom could only occupy certain allowed orbits, each corresponding to a specific energy level. These orbits were quantized, meaning that the energy of the electron was restricted to certain fixed values, with no possibility of intermediate values. When an electron moved from one orbit to another, it would either absorb or emit a specific amount of energy, corresponding to the difference between the energy levels of the two orbits. This explained the discrete lines seen in the hydrogen atom spectrum. The energy released or absorbed when an electron jumped between orbits would correspond to the specific wavelengths of light observed in the atomic spectra. Bohr's model of the hydrogen atom provided a simple yet powerful explanation for the spectral lines of hydrogen. In this model, the electron orbits the nucleus in fixed paths, and when it moves between these orbits, energy is either absorbed or emitted. This energy is quantized, meaning that only certain amounts of energy can be absorbed or emitted, leading to the characteristic spectral lines observed in hydrogen's emission spectrum. This was a direct and compelling answer to the problem that had puzzled scientists for decades. It was a triumph for Bohr's application of quantum theory to atomic structure, and it provided a concrete explanation for the previously unexplained behavior of atomic light emission. One of the key features of Bohr's model was the concept of quantized angular momentum. In classical physics, angular momentum was a continuous quantity, meaning that it could take any value. However, Bohr proposed that the angular momentum of an electron in orbit around the nucleus was quantized, meaning it could only take certain specific values. This was a crucial insight, as it allowed Bohr to calculate the allowed energy levels for the hydrogen atom. By quantizing the angular momentum, Bohr was able to derive a set of allowed orbits for the electron and, in turn, determine the specific energies associated with those orbits. This concept of quantized angular momentum formed the foundation of Bohr's model and helped to explain the discrete energy levels observed in hydrogen's spectrum. Bohr's model was also able to explain the stability of atoms, which had been another long-standing puzzle. Classical physics had predicted that electrons in orbit around the nucleus should continuously lose energy due to electromagnetic radiation and eventually spiral into the nucleus. This would cause the atom to collapse, which clearly did not happen in nature. Bohr's model provided a solution to this problem by suggesting that electrons in stable orbits did not radiate energy. Instead, they only emitted or absorbed energy when they transitioned between different quantized orbits. This concept of stationary orbits, in which the electron does not lose energy, helped to explain why atoms were stable and did not collapse as classical physics had predicted. While Bohr's model was groundbreaking and provided a significant advancement in atomic theory, it was not without its limitations. The model worked well for the hydrogen atom, but it struggled to explain the behavior of more complex atoms with more than one electron. The hydrogen atom, with its single electron, was relatively simple, and Bohr's model was able to accurately predict its spectral lines. However, when applied to more complex atoms, Bohr's model failed to account for the fine details of atomic spectra and the interactions between multiple electrons. Despite these limitations, Bohr's model marked a significant turning point in the development of atomic theory. It was the first model to successfully explain the behavior of the hydrogen atom and the discrete spectral lines observed in atomic spectra. It introduced the idea of quantized orbits and energy levels, providing a new and more accurate way of thinking about atomic structure. Bohr's work laid the groundwork for the development of more advanced quantum mechanical models, which would later be used to describe the behavior of atoms with multiple electrons and the complexities of atomic interactions. In conclusion, Niels Bohr's model of the hydrogen atom was a revolutionary breakthrough in atomic theory. It provided a clear and simple explanation for the discrete spectral lines of hydrogen and introduced the concept of quantized orbits and energy levels. Bohr's work bridged the gap between classical physics and the emerging field of quantum mechanics, and it paved the way for future advancements in our understanding of atomic structure. While his model had limitations and was eventually superseded by more advanced theories, its impact on the development of atomic physics cannot be overstated. It remains one of the most important milestones in the history of science. Niels Bohr's model of the hydrogen atom fundamentally changed our understanding of atomic structure, but it was far from the end of the story. While Bohr's theory was groundbreaking, it also presented several challenges that led to the development of more sophisticated models. Part B of this analysis explores the evolution of atomic theory following Bohr's contributions, focusing on the limitations of his model and how they influenced the development of quantum mechanics, which would ultimately provide a more comprehensive understanding of atomic behavior. One of the most significant limitations of Bohr's model was its inability to explain the spectra of atoms with more than one electron. Bohr's model was incredibly successful in explaining the hydrogen atom with its single electron orbiting the nucleus. However, when Bohr's model was applied to more complex atoms, like helium, lithium, and beyond, it failed to provide accurate predictions for their spectral lines. The problem lay in the interactions between multiple electrons. In the case of hydrogen, the electron's motion could be described by a simple orbit around the nucleus. But in multi-electron atoms, electrons did not behave in such isolated orbits as they interacted with each other through electromagnetic forces, creating a much more complex system. These interactions caused deviations from the simple quantization of energy levels that Bohr had proposed. Another critical flaw in Bohr's model was its inability to explain the fine structure of atomic spectra. The fine structure refers to small, closely spaced lines in an atomic spectrum that Bohr's model could not account for. These lines arise from small adjustments in the energy levels of electrons due to relativistic effects, effects that become significant at high velocities and were not included in Bohr's original model. The fine structure was discovered experimentally and presented a challenge to Bohr's theory. It became clear that a more sophisticated approach was needed to explain the complexity of atomic spectra in atoms with more than one electron. In addition, Bohr's model was also unable to explain the behavior of atoms in strong electromagnetic fields. Under such conditions, the energy levels of electrons could shift, a phenomenon known as the Stark effect. Bohr's model could not account for these shifts, and once again, it became apparent that a more generalized and refined theory was necessary. These shortcomings led to the development of quantum mechanics, a new framework that would ultimately supersede Bohr's model. Quantum mechanics was built on the foundation of Bohr's idea that energy levels in atoms are quantized. However, quantum mechanics introduced new and more advanced principles to describe atomic behavior. One of the most important developments in quantum mechanics was the introduction of wave functions. In Bohr's model, electrons were treated as particles moving in fixed orbits around the nucleus. However, quantum mechanics introduced the idea that electrons do not have well-defined paths. Instead, their positions are described by wave functions, which represent the probability of finding an electron in a particular location at a given time. This was a radical departure from Bohr's idea of fixed orbits and marked a key difference between the classical and quantum descriptions of atomic structure. The introduction of wave functions also led to the development of the Schrödinger equation, which describes how the wave functions of electrons evolve over time. The Schrödinger equation became the fundamental equation in quantum mechanics and provided a mathematical framework for calculating the energy levels of electrons in atoms. Unlike Bohr's model, which was based on simple discrete orbits, the Schrödinger equation allowed for the calculation of energy levels that took into account the complex interactions between electrons, as well as the probabilistic nature of their locations. Another key development in quantum mechanics was the concept of electron spin. In Bohr's model, electrons were treated as point-like particles with no intrinsic angular momentum apart from their orbital motion. However, experiments showed that electrons have an intrinsic form of angular momentum known as spin. The inclusion of spin further complicated the description of electron behavior but also led to more accurate predictions of atomic spectra, particularly for multi-electron atoms. The Pauli exclusion principle, which was developed in tandem with the theory of electron spin, explained how electrons fill orbitals in atoms. According to the Pauli exclusion principle, no two electrons can occupy the same quantum state within an atom, which helps explain the arrangement of electrons in shells and subshells. The development of quantum mechanics and the Schrödinger equation also addressed the fine structure of atomic spectra. The fine structure was explained by incorporating relativistic effects into the quantum mechanical framework, as well as the interactions between the electron's magnetic moment and the magnetic field produced by the nucleus. The inclusion of these effects allowed for a more accurate description of the energy levels of electrons and provided a complete explanation for the fine structure that had eluded Bohr's model. In addition to these advances, quantum mechanics introduced the concept of quantum numbers, which describe the properties of electrons in an atom. In Bohr's model, electrons were simply thought to orbit the nucleus in discrete shells, each associated with a specific energy level. However, In quantum mechanics, electrons are described by a set of quantum numbers that specify their energy, angular momentum, and magnetic properties. These quantum numbers allow for a more detailed and comprehensive understanding of electron behavior in atoms, particularly in multi-electron atoms. Despite its limitations, Bohr's model was instrumental in shaping the development of atomic theory. His concept of quantized energy levels provided the foundation for later developments in quantum mechanics and set the stage for the exploration of atomic structure in greater depth. Bohr's theory also laid the groundwork for future discoveries in quantum mechanics, including the understanding of electron behavior, atomic spectra, and the interactions between electrons and electromagnetic fields. While Bohr's model was eventually superseded by more advanced quantum theories, it remains one of the most important milestones in the history of physics. In conclusion, Bohr's model of the hydrogen atom was a crucial stepping stone in the development of atomic theory. It provided a clear and simple explanation for the spectral lines of hydrogen and introduced the idea of quantized orbits and energy levels. However, it was also limited by its inability to account for the behavior of more complex atoms and the fine structure of atomic spectra. These limitations led to the development of quantum mechanics, which offered a more comprehensive and accurate description of atomic structure. Today, Bohr's model is still revered for its historical significance, and it continues to inspire further advancements in our understanding of the atomic world. Although it was eventually replaced by more sophisticated quantum theories, Bohr's contributions to atomic theory will forever be remembered as a pivotal moment in the history of science. Niels Bohr's model of the hydrogen atom, though groundbreaking in its time, only scratched the surface of what we now know about atomic structure. While Bohr's work provided a solid foundation for understanding the behavior of hydrogen and its spectral lines, his model had limitations that became apparent as scientists began to explore more complex systems. The need for a more robust theory that could explain atoms with multiple electrons, as well as the fine details of atomic spectra, ultimately led to the rise of quantum mechanics. This second keynote addresses the evolution of atomic theory beyond Bohr's model, focusing on the significance of electron interactions in multi-electron atoms and the development of quantum mechanics as a more comprehensive framework for understanding atomic behavior. One of the major flaws in Bohr's model was its inability to explain the behavior of atoms that had more than one electron. While Bohr's model worked perfectly for hydrogen, with its single electron orbiting a nucleus, it failed to account for the complexities of multi-electron atoms. In these atoms, the electrons were not isolated from one another, but interacted with each other through electromagnetic forces. This interaction made the behavior of electrons much more complicated than Bohr's model could explain. For example, the repulsion between electrons in different orbits created distortions in the energy levels of the atom, which affected the spectral lines observed in the atomic spectra. In Bohr's theory, each electron was thought to move independently in its orbit around the nucleus, and the energy levels were determined solely by the electron's orbit. However, in atoms with more than one electron, the other electrons also influenced the energy of the electron being studied. These electron-electron interactions were not accounted for in Bohr's model, which made it impossible for the model to explain the spectra of atoms beyond hydrogen. The theory also failed to provide a comprehensive description of the electron configurations in these atoms, which would later be described by quantum mechanics. The failure of Bohr's model to explain the behavior of multi-electron atoms was one of the key factors that led to the development of quantum mechanics. Scientists began to realize that a new, more sophisticated approach was needed to describe atomic structure and the interactions between electrons. This new theory had to take into account the fact that electrons were not isolated particles but were influenced by the presence of other electrons, as well as the electromagnetic field produced by the nucleus. The discovery of the wave nature of electrons was a critical step in this evolution. The wave nature of electrons was first proposed by Louis de Broglie in 1924. De Broglie suggested that, just as light can behave both as a wave and as a particle, electrons could also exhibit both particle-like and wave-like properties. This concept of wave-particle duality was one of the cornerstones of quantum mechanics. It meant that electrons could no longer be treated as simple particles moving in fixed orbits, as Bohr had done. Instead, their behavior had to be described by wave functions, which represented the probability of finding an electron in a particular location at a given time. The introduction of wave functions by de Broglie and Schrödinger provided a significant advancement over Bohr's model. In the Schrödinger equation, which would become the central equation of quantum mechanics, the electron was described not as a point particle, but as a wave that was spread out over a range of possible locations. This wave function could be used to calculate the probability of finding an electron in a particular region of space. The result was a much more complex and accurate description of the behavior of electrons in atoms, especially in atoms with more than one electron. In multi-electron atoms, the wave functions of the electrons were no longer independent of one another. The interaction between electrons became a central aspect of their behavior. These interactions caused deviations from the simple energy levels predicted by Bohr's model. The electrons in an atom with multiple electrons could no longer be treated as independent particles moving in fixed orbits. Instead, their positions and energies were interdependent, and their behavior had to be described by a set of coupled wave functions. This made the mathematical treatment of multi-electron atoms much more complicated, but it allowed for a more accurate description of atomic structure. The development of quantum mechanics also led to the introduction of the concept of quantum numbers. In Bohr's model, electrons were thought to occupy fixed orbits or energy levels, but the model did not explain how these orbits were filled or how electrons interacted within these levels. Quantum mechanics introduced a set of quantum numbers that described the properties of electrons in atoms. These quantum numbers included the principal quantum number, n, which described the energy level of an electron, the angular momentum quantum number, L, which described the shape of the orbital, and the magnetic quantum number, m, which described the orientation of the orbital. These quantum numbers allowed for a more detailed understanding of the arrangement of electrons in atoms, especially in atoms with multiple electrons. The quantum mechanical description of atoms also led to the development of the Pauli exclusion principle. This principle, formulated by Wolfgang Pauli in 1925, stated that no two electrons in an atom can have the same set of quantum numbers. In other words, no two electrons can occupy the same quantum state. This principle provided an explanation for the arrangement of electrons in atomic orbitals and helped to explain the structure of the periodic table. It also explained the fact that electrons tend to fill lower energy orbitals first, and only when these orbitals are full do they begin to occupy higher energy orbitals. The Pauli exclusion principle was a direct consequence of the wave-like nature of electrons and the quantum mechanical description of atomic structure. As quantum mechanics continued to evolve, scientists discovered that it could explain many phenomena that Bohr's model could not. For example, quantum mechanics explained the fine structure of atomic spectra, which Bohr's model had been unable to account for. The fine structure refers to small splittings in the spectral lines of atoms that arise due to relativistic effects and the interaction between the electron's magnetic moment and the magnetic field produced by the nucleus. Quantum mechanics, with its incorporation of wave functions and the principles of relativity, was able to account for these fine details and provide a much more accurate description of atomic spectra. The development of quantum mechanics also led to the discovery of new phenomena in atomic physics. For example, the phenomenon of electron spin, which had been observed experimentally in the 1920 seconds, was incorporated into quantum mechanics, leading to a deeper understanding of atomic structure. Electron spin provided a new form of angular momentum that was not accounted for in Bohr's model, and its inclusion led to the development of the concept of electron configurations in atoms. While Bohr's model was revolutionary in its time, it was ultimately replaced by the more advanced framework of quantum mechanics. Quantum mechanics not only addressed the limitations of Bohr's model, but also provided a deeper understanding of atomic structure and the interactions between electrons. By treating electrons as waves and incorporating the principles of wave-particle duality, quantum mechanics offered a more accurate and comprehensive description of atomic behavior. It explained phenomena such as the fine structure of atomic spectra, the behavior of multi-electron atoms, and the arrangement of electrons in atomic orbitals. These advancements marked a new era in atomic physics, one that would continue to shape our understanding of the microscopic world. In conclusion, Bohr's model of the hydrogen atom was a significant step forward in the development of atomic theory, but it was limited in its ability to explain the behavior of atoms with multiple electrons and the fine structure of atomic spectra. The development of quantum mechanics provided a more sophisticated framework for understanding atomic behavior, incorporating wave functions, electron spin, and the interactions between electrons. Quantum mechanics not only addressed the shortcomings of Bohr's model but also opened up new avenues of research in atomic physics, leading to a deeper understanding of the nature of matter at the atomic and subatomic levels. Continuing from the previous discussion of Bohr's model and its limitations, this part of the analysis will explore how the development of quantum mechanics expanded and refined our understanding of atomic structure. While Bohr's model made significant strides in explaining the hydrogen atom and the behavior of its electron, it was unable to explain more complex atomic systems, particularly those involving multiple electrons. These limitations prompted the development of quantum mechanics, a more sophisticated theory that has since become the standard framework for understanding atomic behavior. This section will discuss how quantum mechanics addressed the shortcomings of Bohr's model, focusing on the wave nature of electrons, the introduction of quantum numbers, and the development of the Pauli exclusion principle. The first and perhaps most significant contribution of quantum mechanics was the wave-particle duality of electrons, a concept introduced by Louis de Broglie in the early 1922. De Broglie proposed that, like light, electrons could exhibit both particle-like and wave-like properties. While Bohr's model treated electrons as particles that orbited the nucleus in fixed paths, de Broglie's idea suggested that electrons behaved more like waves, existing in regions of space with a probability distribution. This wave-like behavior allowed for a more comprehensive understanding of electron behavior in atoms, particularly in atoms with more than one electron. The wave nature of electrons was mathematically described by Erwin Schrödinger's wave equation, which provided a means of calculating the probability distribution of electrons in an atom. Rather than describing electrons as discrete particles in fixed orbits, Schrödinger's equation treated electrons as waves, and the solutions to the equation known as wave functions provided the probability of finding an electron in a specific region around the nucleus. This was a major departure from Bohr's model, which assumed that electrons moved in well-defined orbits. Instead, Schrödinger's wave function suggested that the electron was distributed in space, with its position being uncertain and described by a probability cloud. This new understanding of electrons as wave functions allowed scientists to explain the behavior of electrons in multi-electron atoms. In Bohr's model, each electron was assumed to orbit independently, but in reality, electrons interact with one another through electrostatic forces. In multi-electron atoms, these interactions between electrons can significantly alter their energy levels and the overall structure of the atom. Quantum mechanics, by treating electrons as wave functions, provided a more accurate model of how electrons in different orbitals interact. The result was a much more complex and detailed description of atomic structure, particularly for atoms with more than one electron. One of the key features of quantum mechanics that Bohr's model lacked was the introduction of quantum numbers. Quantum numbers are a set of values that describe the properties of electrons in atoms. These quantum numbers arose naturally from the solutions to Schrödinger's equation and were essential for understanding the arrangement of electrons in atoms. The first quantum number, the principal quantum number, n, describes the energy level or shell in which an electron resides. The second quantum number, the angular momentum quantum number L, describes the shape of the orbital in which the electron is found. The third quantum number, the magnetic quantum number m, describes the orientation of the orbital in space, while the fourth quantum number, the spin quantum number s, describes the intrinsic angular momentum, or spin, of the electron. Bohr's model, by contrast, only considered the principal quantum number, n, and treated the electron as if it could only exist in fixed orbits. The introduction of the other quantum numbers allowed for a more detailed description of electron configurations and interactions within atoms. These quantum numbers not only explained why electrons in an atom fill specific orbitals, but also provided insight into the atom's chemical properties, such as its reactivity and the types of bonds it can form with other atoms. The quantum mechanical treatment of atomic structure, with its set of quantum numbers, was a far more sophisticated and accurate description than Bohr's original model. In addition to the introduction of quantum numbers, quantum mechanics also led to the development of the Pauli exclusion principle. Formulated by Wolfgang Pauli in 1925, the Pauli exclusion principle states that no two electrons in an atom can have the same set of quantum numbers. In other words, two electrons cannot occupy the same quantum state within an atom. This principle had profound implications for the arrangement of electrons in atoms. It explained why electrons in atoms tend to fill lower energy orbitals first, and why electrons are distributed across different orbitals and energy levels in a way that maximizes the stability of the atom. The Pauli exclusion principle also provided a deeper understanding of the periodic table of elements. The arrangement of electrons in atoms is governed by the Pauli exclusion principle, which helps to explain the structure of the periodic table and the chemical properties of elements. For example, elements in the same group of the periodic table have similar electron configurations, which leads to similar chemical behavior. The Pauli exclusion principle also helps to explain the fact that atoms with completely filled electron shells are chemically inert, as their electrons are in stable, low-energy configurations. Quantum mechanics also addressed the fine structure of atomic spectra, a phenomenon that Bohr's model could not explain. The fine structure refers to the splitting of spectral lines into closely spaced components, which is caused by the interaction between the electron's magnetic moment and the magnetic field produced by the nucleus. Bohr's model, with its simple description of electrons as particles in fixed orbits, was unable to account for these small splittings in spectral lines. Quantum mechanics, however, incorporated the principles of relativity and electron spin, which allowed it to explain the fine structure observed in atomic spectra. Relativistic effects became particularly important for heavy atoms, where the velocities of the inner electrons are significant fractions of the speed of light. In these atoms, relativistic effects caused small shifts in the energy levels of the electrons, which resulted in the fine structure. The incorporation of these effects into quantum mechanics allowed for a much more accurate prediction of atomic spectra and was a major advancement over Bohr's model. Another important development in quantum mechanics was the discovery of electron spin, a form of intrinsic angular momentum that electrons possess. This was a crucial addition to the quantum mechanical description of atomic structure. While Bohr's model treated electrons as point particles with no intrinsic angular momentum beyond their orbital motion, the discovery of electron spin introduced a new form of angular momentum that was essential for understanding the behavior of electrons in atoms. The concept of electron spin also led to the development of the concept of electron spin-orbit coupling, which describes the interaction between the electron's spin and its orbital motion. This interaction can cause shifts in the energy levels of electrons and is an important factor in the fine structure of atomic spectra. The inclusion of spin and spin-orbit coupling in quantum mechanics provided a more complete and accurate description of atomic behavior, particularly in atoms with more than one electron. In conclusion, while Bohr's model of the hydrogen atom was a groundbreaking advancement in atomic theory, it had significant limitations when applied to more complex systems. These limitations led to the development of quantum mechanics, which provided a more comprehensive and accurate description of atomic behavior. Quantum mechanics, with its wave functions, quantum numbers, Pauli exclusion principle, and the inclusion of relativistic effects and electron spin, offered a far more detailed and accurate understanding of atomic structure than Bohr's model. It explained phenomena such as the fine structure of atomic spectra, the behavior of multi-electron atoms, and the arrangement of electrons in orbitals. The rise of quantum mechanics marked a new era in atomic physics, providing a deeper understanding of the microscopic world and laying the foundation for many of the technological advancements of the 20th and 21st centuries. The development of atomic theory has been a cornerstone in the history of science, and it has evolved through numerous groundbreaking contributions from physicists over the past century. Bohr's model of the hydrogen atom was a revolutionary leap forward, explaining the discrete spectral lines observed in hydrogen's atomic emission spectrum. However, as science progressed, Bohr's model was found to have limitations, particularly when it came to explaining the behavior of atoms more complex than hydrogen. This limitation led to the development of quantum mechanics, which refined the understanding of atomic structure and the interactions between particles at the subatomic level. This section addresses three key aspects of the atomic model evolution following Bohr's work: the limitations of Bohr's model, the wave nature of electrons, and the introduction of quantum numbers and the Pauli exclusion principle. Bohr's model was built on the concept of quantized orbits, with electrons occupying distinct energy levels or shells. It worked well for the hydrogen atom, where a single electron orbits a central nucleus, but it couldn't be extended to explain the behavior of atoms with more than one electron. In multi-electron atoms, electrons interact with each other via electromagnetic forces, creating a more complex system. These interactions result in a deviation from the simple energy levels predicted by Bohr's model. For example, in a multi-electron atom, the repulsion between electrons can distort their energy levels, making them different from those in a hydrogen atom. Additionally, Bohr's model was unable to explain the fine details of atomic spectra, particularly in more complex atoms. To overcome the limitations of Bohr's model, scientists turned to quantum mechanics, which introduced a new framework for understanding atomic structure. The wave-particle duality of electrons, a concept introduced by Louis de Broglie, was central to the new theory. De Broglie proposed that electrons, like light, exhibit both particle-like and wave-like properties. This wave-particle duality was a critical departure from Bohr's model, which treated electrons solely as particles moving in fixed orbits. De Broglie's hypothesis was validated experimentally, and the wave-like nature of electrons became a key feature of quantum mechanics. Quantum mechanics describes electrons not as particles in fixed orbits, but as existing within a probability distribution. The behavior of an electron is represented by a wave function, which provides the probability of finding the electron in a particular region around the nucleus. The wave function is a solution to the Schrödinger equation, which is the fundamental equation of quantum mechanics. Schrödinger's equation allows scientists to calculate the behavior of electrons in atoms and molecules, providing a much more accurate description of their position and energy than Bohr's model. Rather than imagining electrons moving in well-defined circular orbits, quantum mechanics describes them as existing in regions of space where the probability of finding an electron is highest. These regions are called orbitals, and their shapes depend on the energy of the electron. The wave nature of electrons also led to the development of the concept of quantization in a different form than Bohr's fixed orbits. Electrons are not confined to discrete orbits. Instead, they occupy orbitals with specific energy levels. These orbitals are described by wave functions that give the probability of finding an electron in a given location. Each orbital is associated with a set of quantum numbers that describe the properties of the orbital and the electron within it. These quantum numbers are essential for understanding the arrangement of electrons in atoms and molecules. One of the most important aspects of quantum mechanics is the introduction of quantum numbers, which were not part of Bohr's model. Quantum numbers describe the state of an electron in an atom, including its energy, angular momentum, and orientation in space. The principal quantum number, n, specifies the energy level of an electron. The angular momentum quantum number, L, describes the shape of the orbital, and the magnetic quantum number, m, gives the orientation of the orbital in space. Finally, the spin quantum number s describes the intrinsic angular momentum of the electron. These quantum numbers are used to describe the distribution of electrons in atoms and how they interact with each other. Bohr's model, by contrast, only considered the principal quantum number, which corresponds to the energy levels in the atom. This limitation made it impossible for Bohr's model to account for the complex electron arrangements in multi-electron atoms. The quantum mechanical model, with its 4 quantum numbers, allowed for a much more detailed understanding of the behavior of electrons. It also explained the stability of atoms by accounting for the interactions between electrons, as well as the electrostatic attraction between the positively charged nucleus and negatively charged electrons. In addition to the introduction of quantum numbers, quantum mechanics introduced the Pauli exclusion principle formulated by Wolfgang Pauli in 1925. This principle states that no 2 electrons in an atom can occupy the same quantum state, meaning that no 2 electrons can have the same set of quantum numbers. The Pauli exclusion principle helps explain why electrons fill orbitals in a specific order and why atoms have the structure they do. Electrons fill lower energy orbitals first, and they cannot share the same orbital unless they have opposite spins. The Pauli exclusion principle is responsible for the unique electron configurations of different elements and is key to understanding the periodic table of elements. The Pauli exclusion principle also helps explain the chemical properties of elements. Elements in the same column of the periodic table have similar electron configurations, which leads to similarities in their chemical behavior. The filling of electron orbitals, according to the Pauli exclusion principle, also explains the stability of atoms, as it ensures that electrons are arranged in the most stable configuration possible. This principle is fundamental to the understanding of chemical bonding and the formation of molecules, as the interaction between electrons in different atoms determines how atoms bond together. In addition to the Pauli exclusion principle, quantum mechanics introduced the concept of electron spin, which was not part of Bohr's model. Spin is an intrinsic form of angular momentum carried by electrons, and it is a key feature of quantum mechanics. Electrons have a spin quantum number that can take one of 2 values, +1, 2, or -1, 2. This spin property plays an important role in determining the behavior of electrons in atoms, as it affects how electrons fill orbitals and interact with each other. The inclusion of electron spin in quantum mechanics allowed for a more accurate description of atomic structure and the behavior of atoms in external magnetic fields. The development of quantum mechanics also led to the discovery of the fine structure of atomic spectra, a phenomenon that Bohr's model could not explain. The fine structure refers to small splittings in the spectral lines of atoms, which arise due to relativistic effects and the interaction between the electron's magnetic moment and the magnetic field produced by the nucleus. Quantum mechanics, with its wave functions and relativistic corrections, was able to explain these fine details and provided a much more accurate description of atomic spectra than Bohr's model. These fine structures are particularly important in the study of heavier elements, where relativistic effects become more pronounced. One of the most important advancements in quantum mechanics was the ability to explain the behavior of atoms in external magnetic and electric fields. Bohr's model was unable to account for the effects of external fields on atomic spectra. However, quantum mechanics provided a comprehensive framework for understanding how atoms interact with external fields. This led to the development of techniques such as the Zeeman effect, which studies the splitting of spectral lines in a magnetic field, and the Stark effect, which studies the splitting of spectral lines in an electric field. Quantum mechanics has also had profound implications in many areas of science and technology. Its application has led to the development of technologies such as semiconductors, lasers, and magnetic resonance imaging, MRI, all of which rely on the principles of quantum mechanics. Quantum mechanics has also been instrumental in the development of quantum computing, which promises to revolutionize computing technology by exploiting the principles of superposition and entanglement to perform calculations at speeds unimaginable with classical computers. In conclusion, while Bohr's model was a major step forward in understanding the hydrogen atom, it was ultimately limited in its ability to explain the behavior of multi-electron atoms and the fine structure of atomic spectra. The development of quantum mechanics provided a more sophisticated and accurate description of atomic behavior, incorporating wave functions, quantum numbers, the Pauli exclusion principle, and the concept of electron spin. Quantum mechanics has not only advanced our understanding of atomic structure, but also revolutionized science and technology. The wave-particle duality of electrons, the introduction of quantum numbers, and the Pauli exclusion principle have had far-reaching implications, shaping the way we view the microscopic world and providing the foundation for many of the technological advancements of the modern era. Quantum mechanics, which developed as an extension and refinement of Bohr's initial atomic model, significantly transformed our understanding of the atomic world. Bohr's model, while groundbreaking, was ultimately unable to explain the behavior of more complex atoms, nor could it account for the fine structure of atomic spectra. These limitations led to the development of quantum mechanics, which offered a more comprehensive and detailed framework for describing the behavior of electrons within atoms. The most important aspects of quantum mechanics, such as the wave nature of electrons, the introduction of quantum numbers, and the Pauli exclusion principle, became essential tools for furthering our understanding of atomic structure and chemical behavior. This part will focus on three key elements: the quantum mechanical description of the electron as a wave, the role of quantum numbers in describing electron states, and the Pauli exclusion principle's influence on atomic configuration. Bohr's model, though revolutionary, was based on the assumption that electrons move in fixed orbits around the nucleus, much like planets orbiting the Sun. This concept of discrete orbits helped explain the hydrogen atom's spectral lines, but failed to explain more complex phenomena, especially in atoms with more than one electron. The model could not account for the interactions between electrons in multi-electron atoms, nor could it describe the finer details of the atomic spectrum, such as the splitting of lines, fine structure, due to relativistic effects. Quantum mechanics emerged to address these deficiencies, with one of its most profound contributions being the wave-particle duality of electrons. The concept of wave-particle duality was first proposed by Louis de Broglie in 1924, when he suggested that particles, including electrons, can exhibit both wave-like and particle-like behaviors. This was a radical departure from the classical view, which treated particles and waves as distinct entities. According to de Broglie, the wavelength of a particle could be calculated using the formula lambda equals frac h mv, where lambda is the wavelength, he is Planck's constant, m is the mass of the particle, and v is its velocity. This wave-like behavior of electrons was experimentally confirmed by the discovery of electron diffraction, in which electrons displayed interference patterns, a hallmark of wave phenomena. This wave nature meant that electrons could no longer be described simply as particles following fixed orbits, as in Bohr's model. Instead, their behavior had to be described by a wave function, which is a mathematical representation of the probability of finding an electron in a given region of space at a particular time. Erwin Schrödinger, building on de Broglie's hypothesis, formulated the Schrödinger equation in 1925. The Schrödinger equation describes how the wave function of a system evolves over time, and its solutions, called wave functions, provide the probability distribution of an electron's position in space. The wave function is denoted by the symbol psi, and its square, psi, 2, represents the probability density, that is to say, the likelihood of finding the electron in a given location. This was a major shift from Bohr's concept of electrons in discrete orbits. Instead, electrons are now seen as existing within regions of space, with certain probabilities of being found at particular locations. The wave function not only describes the probability distribution of an electron's position but also encodes information about its energy, angular momentum, and other quantum properties. These wave functions are subject to boundary conditions, which are determined by the properties of the atom and the interactions between the electron and the nucleus. The solutions to the Schrödinger equation lead to quantized energy levels, similar to Bohr's original model, but with a much more sophisticated description of electron behavior. The probabilistic nature of the wave function also means that electrons do not have a well-defined position or momentum until they are measured. This uncertainty is captured by the Heisenberg uncertainty principle, which states that the position and momentum of a particle cannot both be precisely known simultaneously. This principle further distinguishes quantum mechanics from classical physics, where particles are assumed to have well-defined trajectories. In quantum mechanics, the electron's position is only known in terms of probabilities, not certainty. This uncertainty is an inherent property of quantum systems and highlights the fundamental difference between the classical and quantum views of the atomic world. In addition to the wave description of the electron, quantum mechanics also introduced the concept of quantum numbers, which were not part of Bohr's model. Quantum numbers are a set of values that describe the properties of electrons in an atom, including their energy, angular momentum, and orientation in space. These numbers arise from the solutions to the Schrödinger equation and are crucial for understanding the arrangement of electrons in atoms. The first quantum number, the principal quantum number, denoted as n, determines the energy level or shell in which an electron resides. The higher the value of n, the greater the energy and the larger the orbital. This quantum number is similar to Bohr's concept of energy levels, but it now applies to a broader range of orbitals, including those with more complex shapes. For example, in Bohr's model, the hydrogen atom had only circular orbits, but in quantum mechanics, the orbitals can be spherical, dumbbell-shaped, or more complex in form. The second quantum number, the angular momentum quantum number denoted as L, describes the shape of the orbital in which the electron resides. The value of L can range from 0 to n1, and each value of L corresponds to a different type of orbital, such as s orbitals, L equals 0, p orbitals, L equals 1, d orbitals, L equals 2, and f orbitals, L equals 3. These orbitals have different shapes and orientations, and the electron's behavior is influenced by the shape and spatial orientation of the orbital. The third quantum number, the magnetic quantum number denoted as m, specifies the orientation of the orbital in space. For a given value of L, the magnetic quantum number can take on values ranging from L to plus L, including 0. This number describes the different orientations of orbitals within a given energy level, which are important for understanding the interactions between electrons and external magnetic fields. The fourth quantum number, the spin quantum number denoted as S, describes the intrinsic angular momentum, or spin, of an electron. Electrons have a property called spin, which can take one of two values, +1, 2, or -1, 2. Spin is an intrinsic property of the electron, not related to its orbital motion, and it plays an important role in determining the electron's behavior in atomic and molecular systems. These quantum numbers provide a detailed description of the electron's state in an atom, including its energy, orbital shape, orientation, and spin. They replace Bohr's simpler model of discrete orbits and provide a much more complete understanding of electron behavior in atoms. The introduction of quantum numbers was a key aspect of quantum mechanics that allowed for a more sophisticated model of atomic structure, particularly in multi-electron atoms, where electron-electron interactions become crucial. Another important contribution of quantum mechanics was the Pauli exclusion principle, formulated by Wolfgang Pauli in 1925. The Pauli exclusion principle states that no two electrons in an atom can have the same set of quantum numbers. In other words, no two electrons can occupy the same quantum state. This principle explains why electrons are arranged in different orbitals and energy levels and why they fill orbitals in a specific order. It also explains the stability of atoms, as it prevents electrons from collapsing into the lowest energy state and forces them to occupy higher energy orbitals. The Pauli exclusion principle has profound implications for the structure of the periodic table and the chemical properties of elements. Elements in the same group of the periodic table share similar electron configurations because their outermost electrons occupy similar orbitals. The Pauli exclusion principle ensures that electrons are arranged in a way that maximizes the stability of the atom. This principle also governs the formation of chemical bonds and the way atoms interact with each other in chemical reactions. The development of quantum mechanics, with its wave functions, quantum numbers, and the Pauli exclusion principle, has had a profound impact on the understanding of atomic structure. It has allowed scientists to explain phenomena that Bohr's model could not, such as the behavior of multi-electron atoms and the fine structure of atomic spectra. Quantum mechanics has become the standard framework for describing atomic and subatomic particles, and its applications have led to numerous advancements in technology, from semiconductors and lasers to quantum computing. The transition from Bohr's model to quantum mechanics represents one of the most significant shifts in the history of science, marking the beginning of the quantum revolution that continues to shape our understanding of the universe. Niels Bohr's model of the atom was a landmark in the history of science, particularly for its ability to explain the discrete spectral lines of hydrogen. However, as science progressed, it became clear that Bohr's model had significant limitations, particularly in explaining the behavior of atoms with more than one electron. This led to the emergence of quantum mechanics, a more comprehensive framework that would refine and extend the understanding of atomic structure. The transition from Bohr's model to quantum mechanics marked a pivotal moment in scientific history, particularly through the introduction of key concepts such as wave-particle duality, quantum numbers, the Pauli exclusion principle, and the uncertainty principle. One of the fundamental shifts in atomic theory was the introduction of wave-particle duality, which fundamentally changed how scientists viewed electrons. Before quantum mechanics, electrons were understood as particles with well-defined positions and trajectories, much like the planets orbiting the Sun. Bohr's model was based on this classical idea, where electrons orbited the nucleus in fixed circular paths. However, this concept could not fully explain the behavior of electrons in multi-electron atoms or the finer details of their interaction with light. In 1924, Louis de Broglie proposed that electrons could also exhibit wave-like properties. This wave-particle duality meant that electrons, instead of moving in defined orbits, behaved like waves that could spread out over space. The significance of this idea was later demonstrated by electron diffraction experiments, which showed that electrons could produce interference patterns, a characteristic of wave behavior. This discovery led to the realization that electrons in atoms do not have a specific position or orbit but are instead described by a wave function, which gives the probability of finding an electron in a particular location at a given time. This wave-like behavior was further developed by Erwin Schrödinger, who formulated the Schrödinger equation in 1926. This equation describes how the wave function of a system evolves over time and provided a way to calculate the probability distribution of an electron within an atom. The solutions to this equation, known as orbitals, describe regions of space where the probability of finding an electron is highest. These orbitals, rather than fixed orbits, replaced Bohr's concept of electrons moving in defined circular paths. Schrödinger's wave equation also allowed for the calculation of quantized energy levels, showing that electrons could only occupy specific, discrete energy states within an atom, much like Bohr's model but with much more precision and complexity. As quantum mechanics evolved, the need for a system of organizing the states of electrons in atoms became apparent. This led to the introduction of quantum numbers, a set of values that describe the properties of electrons in atoms. The first quantum number, the principal quantum number n, determines the energy level and size of the orbital. Higher values of n correspond to higher energy levels and larger orbitals. The second quantum number, the angular momentum quantum number L, determines the shape of the orbital, such as spherical S, dumbbell-shaped P, or more complex shapes D and F orbitals. The third quantum number, the magnetic quantum number M, specifies the orientation of the orbital in space. Finally, the spin quantum number S describes the intrinsic spin of an electron, which can either be +1, 2, or -1, 2, representing two possible spin states. Quantum numbers provided a more detailed understanding of the arrangement of electrons in atoms and how they interact with each other and the atomic nucleus. The quantum mechanical model allowed scientists to explain why electrons fill orbitals in specific patterns and how they contribute to the chemical properties of elements. For example, electrons in the same energy level, but with different values of L, occupy orbitals with different shapes, and the Pauli exclusion principle dictates that no two electrons can have the same set of quantum numbers. This rule helped to explain why elements in the periodic table have unique chemical properties, as the arrangement of electrons in their outermost orbitals governs their reactivity. In addition to quantum numbers, another crucial development in quantum mechanics was the Pauli exclusion principle, formulated by Wolfgang Pauli in 1925. This principle states that no two electrons in an atom can have the same set of quantum numbers. In essence, this means that each electron in an atom must occupy a unique quantum state. This principle helped explain the arrangement of electrons in different orbitals and how these electrons fill energy levels within an atom. The Pauli exclusion principle also has significant implications for understanding the stability of atoms, as it prevents electrons from collapsing into the lowest energy state, ensuring that they occupy higher energy levels and thus maintain the structure and stability of the atom. Moreover, the Pauli exclusion principle had profound implications for the chemical properties of elements. Elements in the periodic table are arranged based on their electron configurations, and the Pauli exclusion principle plays a central role in this arrangement. For example, elements with similar electron configurations in their outermost shells tend to have similar chemical properties. The way electrons fill orbitals, according to the Pauli exclusion principle, also explains why certain elements form bonds in specific ways, contributing to the diversity of chemical interactions that make up the material world. In conclusion, the transition from Bohr's atomic model to quantum mechanics introduced key ideas that revolutionized our understanding of atomic structure. The concept of wave-particle duality redefined the way we view electrons, moving away from the idea of fixed orbits to the understanding that electrons exist in probabilistic distributions. The introduction of quantum numbers provided a more precise way to describe the arrangement of electrons within atoms, while the Pauli exclusion principle helped explain the stability of atoms and the chemical properties of elements. Together, these developments laid the foundation for the modern understanding of atomic and molecular physics and paved the way for groundbreaking advancements in technology, including the development of semiconductors, lasers, and quantum computers. Quantum mechanics continues to be the most successful and accurate theory in explaining the behavior of matter at the atomic and subatomic levels, influencing nearly every aspect of modern science and technology. The development of quantum mechanics marked a profound shift in our understanding of atomic structure and the behavior of matter at the most fundamental level. Building upon Bohr's initial work, quantum mechanics introduced concepts that not only refined the atomic model, but also revolutionized the entire field of physics. Central to this shift were several key developments that were essential in explaining phenomena Bohr's model could not, particularly in multi-electron atoms, the fine structure of atomic spectra, and the wave-like nature of particles. These key concepts, wave-particle duality, quantum numbers, the Pauli exclusion principle, electron spin, and the uncertainty principle, transformed the way scientists understood atomic behavior and paved the way for modern physics. One of the most significant contributions to the quantum mechanical model was the idea of wave-particle duality, first proposed by Louis de Broglie in 1924. De Broglie suggested that not only light, but also electrons and other particles could exhibit both particle-like and wave-like properties. This was a radical departure from classical mechanics, where particles and waves were considered distinct entities. According to de Broglie, the wavelength of a particle could be related to its momentum, meaning that the electron's behavior could no longer be fully understood by simply treating it as a particle moving in a well-defined orbit, as Bohr had done. Instead, electrons were described as having wave-like properties, and their position in space was described by a wave function, a concept that would become fundamental to quantum mechanics. The wave function, as developed further by Erwin Schrödinger, provided a way to calculate the probability of finding an electron in a specific region around the nucleus. The wave function is a mathematical solution to the Schrödinger equation, which describes how the quantum state of a system evolves over time. Unlike Bohr's discrete orbits, the quantum mechanical model suggests that electrons exist in orbitals, regions in space where the probability of finding an electron is high. This probabilistic description of electron location marked a departure from the deterministic paths of classical physics and was a key aspect of the quantum model. Another important aspect of quantum mechanics is the introduction of quantum numbers, which describe the various properties of electrons in atoms. Quantum numbers arose from the solutions to the Schrödinger equation and were essential for providing a complete description of electron states. The principal quantum number, n, determines the energy level and size of an orbital, while the angular momentum quantum number, l, defines the shape of the orbital, such as spherical, s, dumbbell-shaped, p, or more complex shapes, d and f. The magnetic quantum number, m, specifies the orientation of an orbital in space, and the spin quantum number, s, defines the intrinsic angular momentum of the electron. These quantum numbers allow for a detailed description of electron arrangements in atoms, replacing Bohr's simpler model of fixed orbits with a more complex and accurate representation of atomic structure. The Pauli exclusion principle, formulated by Wolfgang Pauli in 1925, was another critical concept in quantum mechanics. It states that no two electrons in an atom can have the same set of quantum numbers, meaning that no two electrons can occupy the same quantum state within an atom. This principle explained why electrons are distributed across different orbitals and energy levels, filling the lowest energy levels first before occupying higher levels. The Pauli exclusion principle also helped to explain the structure of the periodic table of elements, as elements in the same group exhibit similar electron configurations, which are governed by the distribution of electrons in orbitals according to this principle. This principle also has profound implications for the stability of matter, as it prevents electrons from collapsing into the lowest energy state, ensuring that atoms remain stable and matter retains its structure. The concept of electron spin, which is closely related to the Pauli exclusion principle, was also developed as part of quantum mechanics. Electrons have an intrinsic angular momentum, or spin, that can take one of two possible values, +1,2 or -1,2. Electron spin plays a significant role in determining the behavior of electrons in atoms and molecules. It explains why electrons fill orbitals in pairs, with each electron in a pair having opposite spins. The inclusion of electron spin in the quantum mechanical model was essential for understanding the behavior of electrons in more complex systems, such as multi-electron atoms, and provided a deeper insight into the chemical properties of elements. Finally, the uncertainty principle, formulated by Werner Heisenberg in 1927, is another cornerstone of quantum mechanics. The uncertainty principle states that it is impossible to simultaneously know both the position and momentum of a particle with complete certainty. The more precisely one property is measured, the less precisely the other can be known. This principle has profound implications for how we understand the behavior of particles at the atomic scale. Unlike in classical physics, where particles are assumed to have well-defined trajectories, the uncertainty principle asserts that at the quantum level, particles, including electrons, do not have well-defined positions or velocities. This inherent uncertainty challenges our classical intuition and reinforces the probabilistic nature of quantum mechanics, where we can only calculate the likelihood of finding a particle in a particular state rather than knowing its exact position and momentum. Together, these five concepts, wave-particle duality, quantum numbers, the Pauli exclusion principle, electron spin, and the uncertainty principle, form the foundation of quantum mechanics and provide a comprehensive framework for understanding atomic and subatomic systems. These principles not only resolved the limitations of Bohr's model, but also offered a more accurate and nuanced description of electron behavior, atomic structure, and the nature of matter. Quantum mechanics has led to revolutionary advancements in technology, including the development of semiconductors, lasers, and quantum computing, and continues to shape the future of science and technology. Its principles are foundational to modern physics and have far-reaching implications for our understanding of the universe at the smallest scales. The evolution of atomic theory has been one of the most remarkable stories in the history of science. From the early models of the atom, such as Dalton's solid sphere model, to the more sophisticated and intricate understandings provided by quantum mechanics, the path to the modern atomic model has been shaped by numerous groundbreaking discoveries. The transition from Bohr's model to quantum mechanics involved many critical developments, especially as it became evident that Bohr's model, though revolutionary, had limitations in explaining atoms with multiple electrons or the finer details of atomic spectra. The 7 key concepts that emerged in the quantum mechanical model wave-particle duality: quantum numbers, the Pauli exclusion principle, electron spin, the uncertainty principle, the Schrödinger equation, and quantum tunneling, each played a crucial role in transforming atomic theory. Wave-particle duality, first proposed by Louis de Broglie, became one of the cornerstones of quantum mechanics. De Broglie suggested that electrons, and indeed all particles, should not only be considered as discrete particles, but also as waves. This was a fundamental shift from classical mechanics, where particles were seen as distinct from waves. De Broglie's idea was supported by experimental evidence, such as the discovery of electron diffraction, which demonstrated that electrons, when directed at certain crystals, produced interference patterns characteristic of wave behavior. This insight redefined the understanding of electrons, moving away from Bohr's model of fixed orbits to a more complex probabilistic description where electrons are treated as wave functions. The wave-like behavior of electrons was mathematically captured in the Schrödinger equation, developed by Erwin Schrödinger in 1926. The Schrödinger equation provided a way to calculate the wave function of a particle, which describes the probability of finding an electron at any given location. Rather than electrons occupying fixed orbits, as in Bohr's model, they are now seen as existing within regions of space defined by orbitals. These orbitals, solutions to the Schrödinger equation, provide a probabilistic distribution of where electrons are most likely to be found, leading to a more accurate understanding of atomic structure, particularly for multi-electron atoms. The Schrödinger equation was a key development because it allowed for the calculation of electron behavior, extending the quantum model far beyond Bohr's simple orbits. The introduction of quantum numbers was another significant step in the refinement of atomic theory. Quantum numbers describe the properties of orbitals and electrons within those orbitals. The principal quantum number, n, specifies the energy level of an electron, while the angular momentum quantum number, L, describes the shape of the orbital. The magnetic quantum number, m, indicates the orientation of the orbital in space, and the spin quantum number, s, describes the electron's intrinsic angular momentum. Together, these quantum numbers allow for a more detailed and accurate representation of the arrangement of electrons in an atom, replacing the simpler orbital description provided by Bohr. These quantum numbers are crucial for understanding electron configurations, which directly affect the chemical properties of elements. The Pauli exclusion principle, formulated by Wolfgang Pauli in 1925, had profound implications for electron arrangement in atoms. The principle states that no two electrons in an atom can have the same set of quantum numbers, meaning no two electrons can occupy the same quantum state. This principle not only governs how electrons fill orbitals, but it also provides insight into the stability and behavior of atoms. The Pauli exclusion principle explains the unique configurations of electrons in different elements and is essential for understanding the periodic table. It also accounts for the fact that electrons fill orbitals in a specific order, with the lowest energy orbitals being filled first, a phenomenon that governs the structure and properties of all chemical elements. Electron spin, a concept introduced in the early 20th century, is another key feature of the quantum mechanical model. Each electron carries an intrinsic angular momentum, or spin, which can be either +1, 2, or -1, 2. Spin plays a critical role in determining how electrons interact with each other and with external magnetic fields. The Pauli exclusion principle, in fact, relies on electron spin to determine how electrons occupy orbitals. According to the exclusion principle, two electrons in the same orbital must have opposite spins, which is why orbitals can hold a maximum of 2 electrons. This feature of electron spin is also fundamental to the formation of chemical bonds and the behavior of materials in external magnetic fields, including the phenomena of magnetism and superconductivity. The uncertainty principle, formulated by Werner Heisenberg in 1927, is another crucial concept in quantum mechanics. Heisenberg's uncertainty principle states that it is impossible to simultaneously know both the position and momentum of a particle with perfect accuracy. The more precisely one property is measured, the less precisely the other can be determined. This principle challenges the classical notion that particles have well-defined positions and velocities, instead asserting that, at the quantum level, particles exist in a state of uncertainty. The uncertainty principle is fundamental to quantum mechanics and has profound implications for the way we understand the behavior of subatomic particles. It highlights the inherent limitations in measurement at microscopic scales, a departure from classical physics that underpins much of quantum theory's probabilistic nature. Finally, quantum tunneling is another fascinating phenomenon that arises from the principles of quantum mechanics. Quantum tunneling occurs when a particle, such as an electron, passes through a potential barrier that it would not be able to overcome according to classical physics. This happens because, as a wave, the electron has a certain probability of being found on the other side of the barrier, even if it does not have enough energy to overcome it. Quantum tunneling has important applications in many areas of modern physics, including nuclear fusion, where it explains how particles can combine to form heavier elements despite the repulsive forces between them. Tunneling also plays a crucial role in technologies like scanning tunneling microscopes, which allow scientists to image individual atoms by exploiting this quantum phenomenon. Together, these 7 key concepts, wave-particle duality, the Schrödinger equation, quantum numbers, the Pauli exclusion principle, electron spin, the uncertainty principle, and quantum tunneling form the foundation of quantum mechanics and offer a comprehensive framework for understanding atomic and subatomic systems. They resolve the limitations of Bohr's model and provide a deeper, more accurate understanding of the behavior of matter at the smallest scales. Quantum mechanics not only expanded the scope of atomic theory, but also gave rise to groundbreaking technologies that have transformed modern life, from semiconductors to lasers to quantum computing. These principles continue to shape our exploration of the universe, offering insights into the fundamental workings of nature and opening new frontiers in science and technology.